For this tutorial, I thought it might be a good idea to show the process of programming the FBX loader and Animator so that I can try to explain a bit about how the parts work as I go. The code for this will be based on a previous attempt that I made, and most of that was based on Wil Motil's code, so he should take credit for that, and some of it's based on monogame's work. As usual, we'll start by creating a project for our target platforms. So I'm going to use the cross-platform desktop. If you want to use advanced HLSL files later, pre-compiled shader objects, you might want to try one of the Windows ones. So maybe I'll just call this example game 3D and hit create. I'm just going to quickly add a little hide folder here and just kind of hide some of this stuff that I don't really want to see right now and drag it into there. And double click on game 1. Using a graphics program of your choice, you can create a little tiny rectangle of gray, which we can use as a default material. I got another one here. I've zoomed up on it quite a bit. This one is gray and white checker pattern, which we can use to check our UV mapping to make sure it's consistent across the surface of our textures. These are mostly for debugging purposes. Actually, the default gray could be used in the case where there's no actual texture, so it'll just default to this gray material unless we want to use this debug texture instead. So we'll add those to our content folder, and to do that you'll have to make sure to set this up for double clicking on it. This I'm just going to say exclude. Okay, so I'll double click on this. While we're in here, let's make sure to add sprite font because we're going to need it for debugging purposes probably. We'll add a new item. Just use a regular font. I just named it font. Okay, I also did a add right click existing and added these two textures here. So we'll save this. At this point in game 1 you'll have something like this. I'm just going to add a bit of code. You can see that I took the underscore off of these two here. So we got font in here now, and I'm going to have a shortcut to graphics device so we don't have to type this out. Just call it GPU. And I made screen width, screen height static here. We could change game 1 to like GM, and then we can, in our other modules, we can just type GM dot if we wanted. I'm going to leave it as game 1 though, just kind of keep things standard. And I added these rectangles, desktop rect and screen rect. I'll show you what those are for later. I'm going to use a separate render target called main target, and I'm kind of using that as my back buffer, which I'm going to stretch out to full screen resolution. Okay, I don't think I need the mouse visible, so I'm just going to turn that off. You can leave yours on if you like. Here I'm capturing the current display resolution. I'm minusing 10 from this temporarily just for debugging purposes. And then here I'm setting up the graphics device. Actually, no, scratch that. We're going to do that in initialize because there seems to be a temporary bug. So we got to set this up like this here, and then we can set those parameters in initialize after. So in initialize, I got the initial screen width and screen height. I get them here. I'm subtracting 14 from the bottom just to get that bar on the bottom so we can debug more easily. I'm setting full screen to false. Once the game's done and we're done with debugging and we want it full screen, we can probably change this to true. And since we're in initialize and we're setting all these like this, we have to do graphics.apply changes. And I'm making sure that the window is positioned in the top left-hand corner. As a shortcut to graphics device, I'm going to say g.gpu is equal to graphics device. I don't think I'm going to use this initial screen width, screen height variables more than once here, so maybe I'll just copy this straight out of here and paste it here. We'll just have to remember when we're done in the game to take this minus 14 off of here. Or if we're going into full screen mode, it won't matter. So I can just delete that then. For the final true back buffer, we're not going to be using depth. We're just going to use, like I said, this main target as our back buffer. That'll have our depth information on it, or our other render targets. Just so you know, every once in a while you might see the code looks like it changed a bit. All I'm doing is pausing it and modifying the comments or the spacing a bit. If I'm actually adding anything or changing anything, I'll let you know. Right, and I added this code here, and this gets the current display presentation parameters, and I'm passing that in over here for our back buffer format, and I'm setting the depth format to depth 24 for our main target. So that's where we're going to render most of our things. You may notice that I put the sprite batch here. Sometimes I need it for passing in to other things I'm initializing, so I usually put it up there instead of down in load. So I'll just take it out of load for now. These are those static variables that are the width and height of our target resolution, which I put up here. We may need those in other places. Same thing with desktop rect and screen rect. We can use those as target rectangles in, like with sprite batch or something like that, and draw to those specific resolutions. So I added this into load so we can load our font. That's really all there is to that so far. And if you look at update here, I added this init in front of it. Just a personal habit of mine. Sometimes if there's something that I know for sure I'm not going to use anywhere else in the code, but it can't be local because we need to keep track. I have this init set to true so that the first time it enters this, it's going to do an initialization phase. So it's something that we don't want to do up here necessarily. So this is just starting off our animations and loading our level, if it is a new level. Level 1 obviously will be loading up here. As far as our inputs goes, I'm just going to use my old input class from my other tutorial. I'll give you a quick review of that and we'll go into using that right away. So I'm just going to go add class and I'm going to call it input. Dead zone is just the area where the analog sticks kind of close to the middle, so just kind of a tolerance range here. We've got a couple of button states, just a shortcut so we don't have to type all this out. If you get anything underlined, you may have to go like this. Make sure you click on the right using so that you get your using up here. And so these are just some other states for keeping track of stuff going on with the mouse or the gamepad, the old game state, so we can compare it to last time to see if it was just clicked, that sort of thing. And as you may remember, if you've seen this before, we pass in the presentation parameters just so we can get the back buffer width, back buffer height, and we do this conversion here. We're also using the target width and height. So we're doing this conversion here to get the true mouse coordinates relative to the target resolution that we're using. If the mouse is on the far right hand side and the target resolution, like the game's resolution, is 1024 in width, we don't want it to say 1800 and something or whatever the display resolution is. We want to report the correct resolution, so we're going to use these scaling values on our mouse coordinates down below. Again, here we're just capturing whether a key was pressed or if it's being held down. Same for buttons on the controller, and we're going to use that in our update, or we can actually use it outside of the update. So for the update, I'm capturing all the old states, like the old keyboard state, mouse state, gamepad state, whether shift or control or alt were down, and we can use that to compare to the current state to find out whether it was just pressed, in which case we'd signal it as control press or alt press or whatever it is. So right after that, then we can get the current state of those devices. And here we're just getting some, like, we don't care whether it's the left or the right shift. We just want to know if shift is pressed down, that sort of thing. So I just got some extra stuff here. You might not need that in your own. That's just up to you. Same with the mouse coordinates. I went a little overboard here. I've got different versions of the mouse coordinates. Like I have a point version, vector version here. The vector version comes in really handy. So if I don't feel like doing a bunch of conversions in a whole bunch of different places, they're already kind of done here. So I just have to pick which one I want. And again, this is just left click, right click, that sort of thing. Just kind of a shortcut way of getting whether the mouse is just clicked or if it's being held down. And we apply the same sort of techniques to the buttons on the gamepad or joystick or Xbox controller, just the same sort of idea. In order to use this stuff, we better make sure we go into game 1. We gotta go here and we gotta add our input class. I always go INP because it's only 3 letters, it's a little shorter, I like that. Going back into game 1, initialize. Let's initialize it down here. Pass in the presentation parameters, which we got here, and the main target. So then it's got the parameters it needs to do the scaling on the mice, or on the mouse coordinates later. So an important thing to remember in update, so that we can actually get accurate updated input information, is to have this input.update in here. I'm putting it right at the top just in case I decide to do some input somewhere in here. This line here now can be replaced with a simplified version. So now it says input.back down, which is the gamepad state for, well, I can just go like this and you can see we've got these different gamepad states that we're keeping track of. And we also check to see if escape is being pressed. For now we're exiting. Later we'll set it to go to a menu and then the user can determine whether they need to exit or not. So in draw, we're going to need to set it to our main target. That's our desired that's our desired game resolution. And then after that, it's going to stretch it out to the desktop resolution. So you can see here, I used to use transparent black. Transparent's the same thing, so you can just use that. We're doing a target clear and a depth buffer clear. So it's going to clear all the colors to transparent. And then in here, we're going to do all our drawing on our main buffer, or I mean our main target, which we're using sort of as our back buffer. And then draw it to the true back buffer here by setting the render target to null. And we can draw it as opaque and just blast it out to the back buffer using the desktop rect as the destination rectangle size. That's that desktop rect that we made up here. Now, for doing 3D, we're going to want to set some 3D device states. So let's make a method here to do that. And I'm calling it set 3D states. I also put this here. We really only need to set it up once, that's why I put it outside. Fill mode solid, cull mode counterclockwise. I'm going to have my texture set up to be non-pre-multiplied, so that's why I have the blend state set to non-pre-multiplied. Depth stencil state, that's default, so it's going to be using depth. If the cull mode hasn't been set, we're going to set the rasterizer state right here, which will set this stuff up. And down in here, we're going to call that method, set 3D states. So we might have been changing states around, we might have used sprite batch, it may have changed states. This just makes sure that everything's set up the way we want it, or the way it's expected to be for the 3D that we're going to do in the lines to follow here. Just kind of looking over the code here. Looks like I got g.pw, that should just be GPU. Okay, I just did a build, and apparently it doesn't like the fact that our icon and app manifest are in this hide folder, so I'll just drag them back out to here. Okay, so I got them out of the hide folder. Seems like I'm finding there's a lot of things in Visual Studio 2019 that aren't as good, and so hopefully I'll find some stuff that's better. Okay, let's try building this and running it. Should just be a black screen right now. Yep. I guess we could do our camera. Scrolling all the way to the top, under display, I'm going to add a camera, I'm going to call it cam, and I'm going to base it off of my other camera class that I made before, but I think this time I'm going to switch the up direction to be the direction most people use, which could mess up the camera class a bit, so we may need to do some tweaking. On the right hand side here, I'm going to go add class, and I'm going to call it camera. So I got the starting camera height. These were going to be constants, but I decided to make it so we could change them if we absolutely wanted to, or if we absolutely needed to, externally, depending on different character sizes or whatever. And I got the head offset starting at the same height at 12. It's going to depend on your character size and your scale, so we'll have to tweak these later. I'm setting the far clipping plane at 2000. Should be good for now. We're going to need the camera position and the target that the camera is looking at, which will be the player. We'll keep track of the view projection and combine them into a view projection here so we don't have to update it all the time. This will keep track of which direction is actually up. We'll keep track of the angle of the camera around the player, so when we rotate it around the player, that'll keep track of that. This is how fast it's rotating around the player when we move it, and this is how far away from the player it is at any given time. This could be adjusted depending on what the player is doing with their analog stick. This holds the normalized direction that the camera is looking. We'll also want to be able to control the camera within the camera class. We have this simple move method here where you can adjust the camera's position by a certain move vector, and then it'll just recreate the viewing matrix by taking the position of the camera, what the camera's looking at, and the up direction, and create the new view projection matrix. Now we probably won't use this, that's why I put this comment here. We're probably going to use an update target instead, and I added that here, and I put this probably will use. So all this is doing is changing what the camera is looking at based on the new target information. So if the targets change positions, then it'll create a new viewing matrix that'll look toward that position. The next method we're going to add is a fairly advanced third-person perspective analog-based camera control. And I'm just pasting this from my old version. I'm going to take out this temporary one here, and I'll just kind of briefly go over what this does again. Here we're just initializing the target for the camera to be the hero position, just getting the thumbstick states, figuring out the forward vector, That's the vector from the camera pointing toward the hero, and getting the x, y, z of that forward vector. So we have this desired height of the camera, where we generally want it to kind of float around that height. And right now I have it set to basically be the same height as the head offset. We might decide to change that later. So what this here does is, well, in the old version, I did it like this. In this version, the camera is not upside down, so we got a different up vector. We got to do the math a little bit differently. So we take the hero position, we add the cam height so that it goes to the same height as the character head, or where we want the camera height to be, which is here. This is our desired height, and so we take the difference between the current height and the desired height, and we multiply that by 0.06, so some tiny amount of that difference, and then we're going to subtract that difference from the current camera height, and that way it'll gradually blend towards the desired height here. So it's only going to do steps of 0.00 or 0.06 each frame. In other words, 6% each frame. And you notice as these two differences become less and less, it starts to slow down. So it kind of works as an ease in. Here I'm checking to see if the camera control has been pressed far enough in any of the directions. In this case, up, down, actually. I got a condition for if it's going in one direction, and a condition here for if it's going in the other direction. Target height is where the camera will go when it gets to the maximum height that it can go up. And I set that to be at the hero position plus the camera height plus 120, so that's the maximum elevation I'd like the camera to have. This doesn't move the camera or anything, that's just saying what the maximum height is. So we say if the camera is below that height, then we're allowed to add to it. And each frame we're going to add 6% of the difference between the current height and the height we'd like it to be. So it'll gradually drift towards that height and kind of smoothly land itself at that height. And this is the old version for the flipped camera. Down here, again, we have the old version here and the new version here. Oh, and I decided to add a ×2 to the dead zones just because I thought it shouldn't be too sensitive. I don't want the camera to jerk up or down if they accidentally push the direction. Probably better just to adjust the dead zone a bit, or have a vertical dead zone and a horizontal dead zone, like it depends. So in this case, we're trying to get the camera to descend, and I just set it so that instead of having this type of variable here, I just have it right here as hero position.y -5. So slightly below the character is the furthest down we want the camera to go. We don't really want it to go into the ground, so it'll be really close to the ground. In this case, the -5 value, you may need to adjust it depending on how tall your character is and what height your camera kind of starts at. Alright, so that covers our up-down for the camera. Then we got a rotation section, which allows us to accelerate the camera, rotating it around the player. So we just change the angle velocity, and I'm going to say minus equals 1/4 of a radian, so that's the amount we're changing the speed that it starts rotating at. And then I have a maximum amount of negative velocity here, being -2 radians. And we don't have this math class yet, so we'll add that in a bit. For now, these will be underlined, but these are just constants for like 2 radians or 1/4 of a radian. Actually, this should be set to -2 radians, unless we want it to go slow. If we want it to go a little bit slower around the player, probably we change both these to 1. Anyway, that's for the keyboard input of rotating the camera. And that's using that less than greater than symbol to rotate it. If we're using the cam pad or the thumbstick to rotate it, we'll check to see if it's beyond the dead zone, make sure it's not centered, in other words, and see if it's going one way or the other way for each direction. For both directions, technically, you're going to take the value of that thumbstick. So if it's in one direction, it'll be negative. If it's in the other direction, it'll be positive. That's why these two lines are the same here, because these values will actually be different. So we get the angle velocity from how far they're pushing on that stick. And again, we have a maximum rotation speed here for each one. In here, you can see I got this math thing. I'm going to change this to math, just to avoid confusion, so we know these are both coming from the math class that we haven't made yet. This one, of course, is capitalized because it's getting a constant here, whereas this is actually calling a method in there, so it's using the class that we're going to make, the object that we're going to instantiate inside this class. To get the radius, we already have the forward vector, which we calculated up here, right? Which is the vector going between the player and the camera. And we got those components in x1, y1, and z1. So this would be the x distance, y distance, and z distance between the player and the camera. And so what we do down here is we go x squared plus z squared, and then we get the square root of that to get the length of that vector. And so that's your sort of your top-down version of that rotation vector, the vector between the player and the camera. We just ignore the y component because we just want to look at it from above and see where it would be, like if it's a line traveling like a circle around the player sort of thing. So we get that radius here, getting the square root of that. We need that radius for doing our rotation calculation here, because we use the radius as a scale, so we multiply it by the cosine of the angle and the sine of the angle to get its rotation around this position, the hero position X, hero position Z. We're also going to be using the radius down here for adjusting the zoom of the camera between where the camera is and where the player is, so to adjust that distance. And like I said, if we're imagining it from the top-down view, we can use the X and the Z component and calculate the current angle of that forward vector using the X and the Z, using minus X and minus Z, so that we get the correct angle here. We'll add to the current angle the angle velocity that we got up here. So we're going to adjust it. And I'm clamping it, the angle, I believe that's making sure it's between 0 and 360 degrees. Not 100% necessary, but you can run into complications if you don't do that. So like I said, the hero position is kind of the origin that it's going to rotate around. So we're using the X and the Z of that. And then the radius is going to scale, like your cos angle is going to be a number ranging from -1 to +1. Same with the sine, just kind of the inverse of that sort of. And the radius scales it, so then it will rotate in a circle based on that radius around this position. And we'll set the angle velocity. So if you're not pushing the direction, well, whether you are or you're not, the angle velocity is going to drop off. It'll only be 90% of what it was each frame. You're not really going to notice it if you keep adding to the velocity up here, but if you let go, this is going to slow down that angle velocity. So the camera will stop rotating slowly, well, kind of quickly actually. It'll kind of quickly stop rotating if you let go of the direction. If you wanted it to be really, really slow, you do something like that. If you want it to be almost instantaneous, maybe something like that. So using that forward vector again, that's the vector pointing from the player, or from the camera to the player. We normalize it so we got a unit direction. So that's just the direction, which we can scale however we like, because it has a length of 1 after we normalize it. And we're going to use that down here. And the way we're going to use it is we're going to scale that direction vector based on the radius, except we want it to be 40 less than, this is greater than 400. It's going to change this adjustment rate to be 1, so it's going to go a lot faster in its adjustment. Normally it's a multiplication factor of 0.02, so only 2%. In this case, it'll really speed it up if the camera's way too far away, and if it's way too close, it'll also speed it up. And that's kind of why we got this -40 here. So if this is like 39, this would be -1. So it's going to back off a bit because it's gone too close to the character. So that's kind of how that works. It's adjusting the camera zoom. And as far as the target goes, we may not want it to look at the target instantly. So what we'll do is we'll figure out the difference between the current target position and the current hero position. See, and this is kind of the reason why I have this only do this once when it first starts, to set the target to be exactly at the hero position, because we don't want it to do that after. So anyway, it's taking the difference between where it is and where it should be, and it's adding to it that difference times 10% basically. Each frame it'll get 10% closer to its mark, and it'll kind of ease in. And that's 10% of its difference, so the difference is different each frame too, and that's why it does that sort of ease in effect. For this one we just add in the head offset because we actually don't want it to look right at the player's feet, we want it to look towards the player's head more so. Then we call update target here. All that does is use our little update target that we made up here to update the viewing matrix based on the new target and the new camera position. And then our shader will be able to use this view projection matrix later to draw our scene correctly. Now the first thing we need to do is create a math class. I'm just going to add that, MAF. This will hold some constants and a couple of useful math methods. Actually, you know what? Let's add a folder. I'll call it math and collisions. Can't use the and symbol. Math and collisions. Okay, let's just drag this into here. We could probably even use math helper pi in here as a substitute. We could even use math helper pi in the other thing if we wanted to. This just has some useful constants in here. We might just use this one, this one, this one, and probably these two here. Epsilon here is used below for this calculation. I'm not sure if I'll need it elsewhere, but I made it available. So we're using this calculate 2D angle from 0 back here in our camera, right here, using the X and Z parts of that top-down vector between the player and the camera, and we're trying to get the angle. This is the math for figuring out the angle using arctangent, and we're using opposite over adjacent, and we're doing epsilon tests. This has to do with each quadrant being a little bit different in its plus and minus. However, if we use this, is basically the same as this, which calculates to angle using the vector. And I believe the quadrants are all kind of handled inside this. So that's why this is using atan2. And here I'm just kind of directly calculating everything with atan. So this is just based on an older method. It probably wouldn't matter if you used this one or this one. And down here I got this as a static class for math extensions. So in this case, if we have a vector, we can just put .toAngle on the end of it and convert it to the angle amount as a float. And we'll be able to add other public static methods down here, which we'll be able to access from anywhere without having to create a new object each time. This is just their clamp angle, and it just makes sure that our angle is going to be between 0 and 360 degrees, which is between 0 and 6.28 radians. 360, that's how it gets that there. Alright, that is all there is to math. Let's go back into game 1. Okay, so we have this camera class now, but I realized that we forgot to make a constructor for it. So let's go back to the camera class and add a public. Let's pass some stuff in here for setting up the camera. We'll pass in a graphics device as GPU, we'll be using that, and a up direction and input, and we'll reference it with this. Actually, you know what, right now we don't need GPU in here. We'll just take the up direction and the input. And then we'll set the camera starting position and the target. And I just picked a random place on the map that's 12 units up from the ground. The target initially is just looking at the very center of the world at the ground. And we're gonna need a math in here. Let's make sure to put that right here. Actually, we're going to call it math just to avoid confusion because the class is called math. And then I'll just set it up here in the constructor. And this position and target won't really matter because that's going to get set right away when the camera update is called for update player cam down here. No big deal where you put this. Okay, and I added this block of code here, creating the viewing matrix using a create lookat with the position of the camera and the object that the camera wants to look at, the target. I'm giving it the up direction, and the projection matrix, we're creating a perspective field of view. I'm using pi over 4 for now, which is a 90-degree viewing angle. Oh, I actually do need to pass in the GPU here, because we're going to use it here just to get the aspect ratio from the viewport. And you never know, eventually we might want to reference it and use it for other things in here. So I'm using a near clipping plane of 1.0, just remember this cannot be 0, and a far clipping plane, which we set in our constant here as 2000. So if we decide to change that later, we don't have to look down here or anything, we can just change it at the top. And we also pre-compute the viewing projection matrix combined. We should probably also initialize our unit direction, so that's the forward vector of the camera with a length of 1. So to do that, all I did was I got the viewing matrix, got the forward vector for the view, and then I make it a length of 1, and we can scale that elsewhere so that we can basically make a radius between the player and where we want the camera that follows along that desired direction. So now let's go back to game 1 class, and we'll go to initialize, and we'll set that camera like so. And this time we're using the actual normal up direction. So, and the reason for that is because the objects this time are all going to be facing the other direction. Okay, let's go down into update and make sure we update the camera every frame also. So perhaps right here, say cam, update, player camera based on a hero position. At the moment we don't have a hero position, so let's scroll to the top and we'll just add one in here. Vector 2 hero position. Okay, so we're also going to have a matrix hero rotate, and I set the hero position initially to be somewhere near the center, just a hair above the ground, and I started these constants that we were just like we were doing before in the other tutorials, where I can have different constants that represent, I can use them as indexes, and it's just a little shorter than writing out an enum, and a little more convenient in some ways, partly because we can avoid casting. Eventually, what I would probably do is start an actor class, and all your characters, your enemies, your NPCs, the main characters, they can all run based on the same principles, where you got the position, the rotation, etc., etc. Okay, so at this stage, everything is set up. If we wanted to, we could create a separate type of model, like a monogame model, and we could load it and render it down here and test out our 3D stuff. This is based on my other test code, so I'm already aware that it's going to work. We're just going to go ahead and start making the FBX loader now. So this is probably the part of the tutorial you wanted to get to. For our model, I'll probably make our own custom bounding box. So I'm just going to start a bounding box class here. I'll call it bbox. And this should be in the math and collision section here. Okay, we'll have to be using Microsoft XNA framework, and right now all it does is construct and collect the information about the minimum and maximum values, so the two opposite corners of the bounding box, which will be used to determine chances of collision or whether it be clipped from view, that sort of thing. Can probably do this and just make sure to save that. Next we'll go over to our solution here, right click, and we'll add a folder, and we'll call this folder SkinModels. So any models with skins, we can put stuff to do with that in here, and any of the classes that handle that sort of stuff. So going over top of the SkinModels folder, let's add class SkinModel. Okay, so this is going to be based on work done by Wil Motil, so we'll just make sure to put a credit in here and a link to his work. In each one of these classes I'm going to have a settings section where we can change some constants for certain kinds of warning messages. So here I got warning missing diffuse texture. I set it to false because we're just going to override it if it's not there. But in a game you might not want a situation where there's missing diffuse texture, so you might want that turned on at that time. So kind of optionally I got this debug texture stuff in here. That's that checker pattern. I got a boolean that we can pass in from the loader. If we want to use the debug texture, then it'll resort to using this just to make sure we got even UV coordinates. This is optional to use, and I'm setting max bones to 180. This just depends on how we set up our skin effects and how many bones we want to put in there. So I'll leave that up to you. I thought I probably would never use more than 180. I think I'm usually using around 125. So I'm going to go over what our model class is and what it's going to do for us. So as you are aware, your character has a skeleton, and there's a root bone, which is the starting parent for all of the other bones. For example, these two clavicle bones are parented to this chest bone here, and these base digit bones are all parented to the hand. In this example, we're going to assume the origin is here at the feet. The pose where your skeleton starts at, this pose you're looking at now is called the bind offset pose, or the bind pose of the character. First of all, we'll need to create a list of matrices that will make up the skeleton, which will basically be matrices that make an offset point from this origin here. So the first one, being the root, would just offset it to here. And then each matrix would create a distance and orientation to create the vectors that make up the bones, connecting them. So for example, the next bone here would inherit from this bone, effective the matrix for this one. And that's just for the calculation part of it. So basically what you're doing is you're creating these offsets to get to each bone position. And those are your bone bind offsets. Again, the bind pose being the initial pose of the character. One thing to keep in mind is we got all these vertices. For example, I got the wrist here, and some vertices will pretend to exist around the wrist that make up the triangles. And we want to move and rotate all of these little vertices relative to the original bind position of the character. And the reason we want to do it that way is because all of the geometry of the original character is relative to that bind pose. We need something that's going to transform these vertices correctly. We can't just do bone relative transformations. And the reason being is we don't know where those vertices are going to exist relative to different bone locations, especially considering we're blending the influence between different bones depending on how much each bone bends and how much percentage influence a bone has on each vertex. So this one could be 20% influenced by this one and probably 80% influenced by this one here. And that way it folds nicely and it's not going to be a sharp edge when the arm bends. Same on the back of the elbow. You'll notice that the geometry stretches out as the elbow bends. That's because the vertices along the back will have partial influence between the two bones. That percentage influence we call a bone weight. Our shader will allow up to 4 different bones to influence each vertex. If you wanted, you could potentially make it so that it can support more, but 4 is generally what's used in most games because it's pretty efficient and you usually don't ever need more than 4. So let's say we have this pose here, the red arm, and we want to rotate all of this to get to where the green arm is. We need some way to interpolate between these two poses. So each bone has an animated rotation, which is parent relative. So basically, this bone here, in order to get this angle, is going to rotate to something like this. Maybe less than that actually, probably to about here, because when we add it to this, it's going to inherit some of this angle, and that's going to make it rotated more this way. Now, in order to rotate it though, just as a simple example, if we wanted to rotate from this bind position to here, what we got to do is we got to pretend that this is here actually, and we're rotating to here. And then we multiply by the parent to get it so that it's here. That'll end up creating this here. I guess another way to say this is, let's say, just remember that each bone was put at an offset, and from those we could generate the inverse offset, which gets from that bone position to 0. Because for a rotation to work properly, for example, let's say if we choose this bone here and we want to rotate it. If we were to rotate it right where it is, then it would rotate around 0, which is here, which is not what we want. We want this to be the origin, so to make that the origin, we have to translate it so that it's at the origin right here. That way, when we apply our sine and cosine rotation in the matrix, it'll actually rotate it correctly, so that it's relative to this 0. Then, to add it on to the parent location, for example, if I was just rotating from the bind pose here, I would just multiply this by the parent matrix, and that would move this resulting one to here so that it's attached right here. So if you consider what that's doing to the vertices, like one of these for example, our bone gets translated by that inverse offset matrix to here, and this point would be here. So that would be this point here, would be here, for example, and maybe this point here would be here. And then those rotations would be also applied in the same sort of way. So they'd rotate with the bone. And that it's doing that part in the shader. It's using those matrices and applying them in the same sort of way to these vertices so that they rotate the same way. And then this all has to be relative to the parent. So to inherit the parent's rotation effect, we multiply this by the parent matrix. And what that ends up doing is these, this one, and this one, just like the bone here, will get transformed so that these rotations are inherited, so that this new rotation is rotated even more because it's added on to the rotations of these ones. So then this bone gets placed here, and these points also are going to inherit those rotations and offsets based on the effects of these matrices combining. So matrix math is kind of magic that way. The effects of each one kind of stack up. So that's essentially kind of the idea of how it works. And there's different ways that you can do it in different orders that give you the same results. Okay, let's go back to doing some coding here. I may go back to some drawing references later, periodically, just to kind of explain things a bit better in case they were a little bit fuzzy, which they probably are. We're going to have a list of our skin shader matrices. Those are the matrices that represent the transformation of each bone when it's finished figuring out what those transformations are going to be. And those are going to be passed into the shader, and it's going to use a percentage based on the vertex weight of how much rotation to apply to each bone, and it'll use these. We're going to have a list of meshes. We don't have a class for this yet, so this is just, same with this, we don't have this class yet, so I just have them commented for now. With this type of skin model system, we can actually have multiple meshes. We don't have to have our skin mesh consolidated as a single skin mesh. And we're going to keep track of our root node. So we got this bone here, calling it model node. That's the module we're going to use, which is going to represent the root of the tree. So bones and nodes are kind of interchangeable, but technically a mesh can be used as a node. So they tend to refer to them as nodes rather than bones, just to clear up what they mean by node here. So I haven't played around with multiple animations in a file, but you could have multiple animations inside one of these, and we keep a list of those, and we keep track of which animation we're currently using. Here we can keep track of the current keyframe and whether or not animation is running, whether or not we should loop the animation, like for a run cycle or walk cycle, the start time in the timeline for the animation, the current animation frame time, and I guess these are kind of straightforward based on their names. And here, like this is commented, we have this override animation frame time. We can set this for the purpose of testing particular frames and stepping through frames. And that's useful for debugging purposes. So we can see, for example, whether the last keyframe joins up with the first keyframe nicely, if it was a looped animation. We're going to have some classes like skinmesh. Some of these ones in here are only going to be used inside the skin model itself. So we may as well make those into nested classes. So let's add one for the model node, for example. Actually, before we do that, let's make sure we add Assimp as a reference. So we're going to be using assimpNET, and as these comments here say, is a cross-platform .NET wrapper for Open Asset Import Library. We need to add the assimpNET NuGet to the solution. So in the solution explorer over here, we're going to right-click. We'll look for Manage NuGet Packages, and we're going to use Browse and type in assimpNET. Okay, I'm just going to use this version 4 here and click Install. Okay, I added in this model bone class. You might want to rename it because we got an X and A model bone class also, but it seems to be resolving okay, so I'm just going to leave it as is. As I was trying to kind of explain, the model nodes are basically like bones, except they could be meshes or other things. They're not necessarily bones, and each one could affect more than one mesh. So we got to keep track of that, and that's what we use this for. Each bone has a local matrix, which is basically just the rotation of that bone by itself. So if it was rotating around 0, this would be its local matrix that does the rotation or transformation for that. And then the combined matrix is the accumulated transforms down along the bone tree, basically. Sometimes that's referred to as the global space transform, and the shader will end up using that one. So basically, in each one of these, there could be a few of these model bones. These are basically, you could pretend they're actually inside here. Each one of these has a name index of which mesh it is going to affect and which bone it is out of the bone list. So basically what that's going to do is we're going to loop through the unique mesh bones for the node, and we're going to do that in the update, and we're going to loop through them and use the bone's mesh index and the bone's bone index. So this here is actually, this BN is actually the unique mesh bone in the list if it's looping through. And then we can apply to the meshes based on the mesh index the updated matrices for the shader matrices for that mesh based on the bone index also. So then we can say bone index offset matrix times the combined matrix. That's the combination of the effects of all the matrices. We'll get more into this stuff later. I'll try to explain it better later on. So for each of these bones, we're having a offset matrix, which is the distance between the origin and where that bone starts in bind space. The offset matrix is the vector that takes us from the origin to where that bone is in bone space, or I mean in bind space. And we're going to need the inverse offset matrix so that we can do our rotations around the origin. So we have this inverse offset matrix, which gets the the inverted version of the offset matrix. Number of weighted verts is how many weights apply to this vertex. Could be 2, could be 4. We're allowing up to 4 in our shader. And if I expand these definitions here, if you want, you can pause the video and try to read this. There's a lot to take in. So sometimes people say model pose and bind pose. Usually they mean bind pose, and that refers to the pose of the skeleton in relation to the original geometry of the character. Bind space refers to where the vertices are if it's in bind pose. Bone space refers to local bone orientations, sometimes referred to as local space. Local space, though, sometimes is referred to as model space. So the terminology can get a bit confusing. It just depends on how people are using it. Global space usually refers to the combined matrices. The global transform is sometimes referred to as combined transform. That's all the bone transforms combined into one matrix for a bone. So the final effect of the matrix combination is placed into one matrix. Combined transform often refers to the animated combined matrix after combining all the matrix transforms, and the animation of the local transform. Animated transform refers to the same thing, although sometimes animated transform can refer to the local animated transform. So it just depends on context, I guess. And world transform often, again, refers to global transform. However, this can also mean the very final transformation done on the shader, placing it into world position, after which then just the projection and view matrix will affect that position. And the offset matrix we went over before, that's getting from the origin of the character at the base of the feet, for example, up to the shoulder or to the elbow or wherever. And then the inverse does the reverse. It can take a bone with a local rotation, it can move that bone down to the base of the feet, rotate it, and then we can transform it to where it's supposed to be. So we can move it back and forth from those positions using the offset and inverse offset matrix. And again, that's to get correct rotations. The local transforms or local animated transforms are our key transforms essentially, and those rotate vertices with the joint around a parent. So it's in relation to the parent, and we do that as if the parent were at 0, 0, 0, so that the rotation is correct. And again, when that's combined with the matrix for the parent's global transform, then it'll all be placed where it should be instead of at the origin. And it'll inherit those angle differences that the parent has. And as I mentioned, offset matrix gets us to bone space, but we need to get back to the origin using the inverse of the offset, so we can properly rotate the vertices. Matrix calculations are needed, which transform bones and vertices from bind position to origin and then added onto the parent's combined animated transform. I'm basically just saying the same thing again here. I have all this in this video tutorial. That's a lot of extra comments, so I'm just going to take it out because I don't really think it's that necessary. Okay, so now we got our model node and the bone mode, or model bone, which it needs. And so now we can have our root node of tree uncommented, and we can make some more of these nested classes. Just going down under class model mode, I added this next class, the class skinmesh. First, I'll just address what's going on here. I got this vertex normal map skin. If you wanted, you could use the regular way of saying this, which would be like vertex position normal texture, as I'm sure you're familiar with that, and then add skin or something else on the end of this to signify the other entries that this vertex declaration type will have. We haven't made this type of vertex yet, but we're going to add it shortly. By the way, this isn't supposed to be in here. I just added this as an example. Models are composed of meshes, each with their own textures and set of vertices associated with them. Looks like I got a spelling mistake there. I don't want to go into too much detail as to what these do. I just want to give you a brief outline so you're kind of familiar with what's going on, what we have in here, why it's in here, and what we're going to use it for. It's possible that our mesh or whatever, it's possible that the base node mesh could have its own animation transform associated with it. We may need to move the root position or the mesh itself. So we got this node with animtrans. We're going to initialize it as an identity matrix, but if there happens to be a animation transform, this will keep track of that. We'll show more on that later. The old code had this get mesh node's name, which returns the name of it. Since this is public, I don't know if this is really necessary. I'm not sure we're actually going to use this, so I'm just going to comment it out. I might actually delete it later. It might be useful for debugging purposes somewhere. Actually, I'll just delete it for now, and I'll add it again later if it turns out I do need it. And each skin mesh has a name, a mesh number, whether it has bones, whether it has mesh animation attachments, and then we got our regular texture name, our normal map name, a height map name if we're using one, reflection map name if we're using one. Then we have our texture diffuse, texture specular, texture normal, height map, reflection map. There's options that we could add for light map or ambient occlusion. I'm not actually going to use ambient occlusion. I'm just going to bake the sort of ambient occlusion into the diffuse texture map anyway. And as far as other lighting goes, like dynamic lights, I'm probably going to just go with a different shader or an extended shader that'll do a little bit more, so it'll allow for shadow mapping. I will leave these comments here though, and these comments here as a reminder that these are things we could easily add in the future if we wanted, or if someone wanted. I probably won't use most of this stuff. So we got our vertex list, which is going to go into our vertex buffer, or VAO, and our index list, same sort of idea. Those are the indices that select the vertices that make up the triangles. So essentially this right here will hold all our mesh data. This here holds the list of bones that correspond to this mesh, and these shader matrices are the final shader matrices that will be passed to the graphics card to be used to influence the bones of this mesh. This combined final transform, it's returning node with animtrans combined matrix. So basically what this is it's going to combine with whatever other world transform we're applying to this particular mesh and get the final transformation of the mesh. So there could be a world coordinate for the character. The mesh could have its own local transformation. It could even have its own local animated transformation. And this will combine with that world transformation and move everything to where it should be. We'll see more on that later. So this isn't actually a combination of matrices through the bone tree or anything like that. This has to do with the mesh itself. Here, if we want, we can store our min, max, and midpoint of our vertices. And each mesh or submesh has its own material index and material name, which is useful for identifying which part of the character it is, or if it's an attachment or something like that. Here we have the default color settings for our ambient, which is our minimal light. I didn't want to put it at 0, but it would probably start off really dark. We got it at 1, which is maximum. When it loads the character and the materials, though, it's going to override all these values. These are just defaults. So then we got our diffuse material color, and like a lot of this, you won't notice unless you actually turn the texturing off. For example, your diffuse color. We got our specular highlight color, our emissive property, how see-through it is, how reflective, the shininess, the shine strength. I have commented here probably specular power. Can use to narrow and intensify highlights, make it look more wet or metallic looking. We got our bump or normal map scaling to amplify or reduce, whether or not it is two-sided, which might be used for something like glass or ice. And there's some other ones we might potentially want to add in the future if you decided you needed them. I just left them as comments here. Alright. And now if we scroll to the top, we can uncomment our skin mesh meshes, because we have that now. And from the looks of it, we should probably have a rig animation, which can also be nested because we're probably not going to use it outside of this. I'll uncomment it, but it'll be underlined. So we'll come down to here and start adding it. So under skin mesh, I added this class rig animation. All the animation nodes are in rig animation, and the nodes have lists of frames of animations. So basically a mesh can have its own frames of animations. There probably won't be any in ours, but our bones will. So each of those bones will have a list of animations. Okay, so for the rig animation class, we got our animation name, how long the animation is in ticks, also in seconds, and this is the duration if we pad it with some extra time, and it's in units of seconds. So we may want to add a tiny bit of extra time if it's a looped animation, just to smoothen it out if it wasn't exported to loop properly. So that can be adjusted. We got our ticks per second, total number of frames. Like a lot of this is kind of self-explanatory. I'm going to take out this frames per second thing here. I'm not using it in here. Could add it back in when we need it. We don't have an AnimNodes class yet, so we'll add that. These are just a couple booleans, whether the mesh has animations, has node animations. I mean, you could have something that is just a mesh that's moving around or something, and it doesn't have nodes, so that's possible. Okay, and also we have the interpolate, which interpolates or blends between keyframes, and it also takes AnimNodes. So maybe before we move on to the rest of this class, we'll come back to this. AnimNodes is fairly small, so we'll just add it. It's another nested class. So we'll just go down here and add it in down here. So here we have a reference to which node this is for, and a node name can be placed in here. And we got our list of positions, scales, quaternion rotations. We're using quaternions to rotate rather than matrices for the rotation interpolations themselves. That way, if we use what's called a SLIRP, spherical linear interpolation, SLERP, if we use that with the quaternions, we should get a smooth rotational interpolation, and it won't give us unexpected results. If you use Euler angles, matrices, the normal way, you could get weird results where it's trying to interpolate the wrong direction. We also have a list of positions and scales. So these are the corresponding times: position time to position, scale time to scale, and rotation time to rotation. So basically this is just holding a list of keyframes for this node. Now if we go back up here, we now have these, so they're no longer underlined. And when we interpolate, we get the animation time, the time that we're at, and the node that we wish to interpolate. And what that will do is it'll interpolate between the current keyframe and the next keyframe for this node. So here we make sure we get the duration in seconds, and that's a double. And if we want, we can pad it with this extra duration so that the looping is smoother. We'll go into setting that up later. If the current animation time, that's where the playhead is in the timeline, if it's exceeded the entire duration of the animation, it just loops back. So it subtracts that amount, that length amount. Now we've got to make sure that when we declare these, that we give them all the values, the compiler doesn't complain. And we get the first quaternion rotation to be from keyframe 0 for all of these, and we're doing that for position, scale, rotation times, so on and so forth, and just doing the same thing for the second keyframe on this side. And then we'll go down below and test some conditions and decide how to change those if we need to. So this first whole section here is for getting the rotation, which is primarily what we'll be doing with the animation. There's a possibility too that there may be some position change and some scale change. So let's go to the rotation one. And first we get the end time index as being technically we could get this, qrot_time.count -1, and stick it in here. I just thought it's a little neater to have this nt index, and I thought I might need it again, but I don't think I did. But I think it looks a little better like this. What we really just need is our end time. Oh, but the end index, which is the final rotation frame, we will use that more than once in here. So it's actually good that we capture that here. So for our end time, that's the final rotation time, we use this index here. Now, if the animation time right now is greater than the last keyframe's time, then we'll set it to interpolate between the last frame and the first frame for animation looping. To do that, we'll set the time rotation frame to be the end time, and the second keyframe to be the end time plus, I should kind of explain this. This part might be a bit confusing. So right now, this is set to the time for keyframe 0. So by going plus equals duration in seconds, that puts it right at the very end of the maximum duration of the animation. And so if there is some padding added, it can continue past the end time here for a certain amount so it can do its looping properly. So as I said, this will be for time 1. We'll have a corresponding, that's using end time, and we'll use the end index, which corresponds to the same spot on the timeline, and we'll get the Q1 or keyframe 1 rotation. So this might be a bit confusing because what it's doing is it's actually rotating, but it's extending the duration on the timeline. And Q2 will be pretending that there'll be a copy of frame 0 that's basically past the end of the timeline, which will be Q2. A bit confusing, but the regular keyframe updates and animation are a little bit more straightforward. easier to understand. So this is the regular case scenario where we're not looping the keyframes. First of all, we set frame 2 to be the end index, and we're going to loop backwards until we find an appropriate spot on the timeline that's after frame 1. Technically, we could keep track of where the current keyframe is and always have it progress in a certain direction, but with the way this is set up, it'll allow you to just move the playheader or the position in the animation anywhere you want, backwards, forwards, any amount of distance, and no matter where you move it, it'll be able to set up an interpolation between the keyframes. As long as you don't have thousands of keyframes, it's probably not really going to make any noticeable difference. But like I said, if your animation is always going to be sequential, you could set it up the other way too. The way this loop works is we're checking the rotation time for the quaternion at this frame 2, and t is going to represent the time that it finds at frame 2. And so what we do is we keep reducing frame 2, causing this time to be less and less and less. And we check each time to see if t is less than anim time. So this actually, reading it this way, could probably be a bit confusing because we're checking to see if anim time is greater than t. So maybe I'll actually just reverse this. Is t less than anim time? It's the same thing basically. We're checking to see when this time is finally going to be less than anim time. When it gets to the point where it checks it and yeah it is, then we break out and then we add 1 on to frame time because we went 1 too far. So that's what we're doing here. If however frame 2 is at frame index, if these are the same, then we don't want to add to frame 2 because it's already at the end. And so now we know for sure that we've got the keyframe that comes after the current keyframe, and we can get the time for that keyframe right here and the actual value for that keyframe right here. And normally frame 2 will always be 1 greater than frame 1 at this point, but what if both frame 1 and frame 2 are now 0? We would definitely need to make sure that frame 1 is looping from the end frame actually. So we'd say -1 and then check to see if it's less than 0. If it is, then we set frame 1 to be the last index, so frame 1 is actually going to start at the end of the animation and it's going to loop around. And since this is the last time in the timeline, we minus the duration in seconds so that this is going to occur before frame 2. And remember that there's padding on this, or there's probably padding on this. There'll be some space between those keyframes. And if we're not doing this reverse loop thing here, we just do the usual. We set the time for frame 1, and then we get the rotation at frame 1. So now we have the rotation amount and the time for keyframe 1 and keyframe 2 from this section that I've highlighted here. We're going to apply the same techniques to get the position keyframes and the scale keyframes. So again, we get the end times, except this time we're using those variables, but assigning them based on position time and position. If the animation is beyond the end time, then we want to loop it. So again, keyframe time for position 1, or keyframe 1's position is going to be the end time. This one, as you may remember, is already initialized up here to be for frame 0. So we add on the duration in seconds, and that should give us some time that's slightly after this end time here. And then again, we just get position 1, and I probably forgot to mention too that we don't have to get position 2. We already have it here. It's at keyframe 0. So that's why I didn't do that in the rotation part too. Q2 is already 0, so it's already set up for looping. So if we're not looping, then we do the usual like we did before. We count back from frame 2 to find a time. I'm going to change this around again. I just find it less confusing if I say time is less than animation time. So it counts back until it can find a time where frame 2 ends up sampling a time that's less than the time for frame 1. And then it knows that it's gone too far, so it adds 1 to it, and now it has the frame that comes right after the current frame. So again, we sample the time for keyframe 2 and the position for keyframe 2. And we do a test to see if we're going to have a backwards loop going on here. Same thing as before, just for that. If not, we can sample frame 1 position time here. And either way, we're going to get the position 1 at frame 1. And for this section here, we're doing the exact same thing except for scale. So you got to remember to replace scale time, scale time here. And these all got to be TS and S if you're using the same variable naming that I'm using. Just remember to change this one, and this one, and this one. And then down here, what else you got to change? Scale time. A lot of the same variable names. S2, TS2, TS1, TS1, and S1. All right, let's move down. I got these three floats here: time quaternion rotation interpolate, time for position interpolation, time for scale interpolation. So we'll start with a quaternion. We get the time by saying get interpolate time %. That's the value between 0 and 1. I like to think of it as percentages, 0 to 100%. So we supply a TQ1, time for keyframe 1 for the rotation part, and the time for the keyframe 2, and get what the actual animation time should be between those two time points. So we're using the animation time passed into this interpolation method to figure out where that actual time should be between these two. And then down here we can use that value as our percentage amount between the two different keyframe values for the rotation, using the quaternion slurp, spherical linear blend between two quaternions. This will give us a nice smooth rotation between these two values over time as it animates. We have not added get interpolate time % yet, but we'll do that after I finish off with this method. So you could copy and paste these and do the same for position and scale. Just remember, this is vector3p, and this needs to be changed to TPI, TP1, TP2, and then you can say p is equal to vector3 lerp, p1, p2. So that part's quite a bit different actually. This part's pretty much the only thing you'd be copying. And then TPI for the time for position interpolation. Doing the same thing for a vector3 scale, TSI, TS1, TS2, and then scale is equal to vector3.linear interpolation, lerp, S1, S2 using TSI. So now we can create a matrix scale, matrix rotate, and matrix translate. So we say ms equals matrix dot create scale for s, the scale value we got, and then matrix rotate, matrix dot create from quaternion, the quaternion that we got up here, and matrix translate, mt is equal to matrix dot create translation from p, the position. And then we can calculate that matrix, the final matrix, by saying m is equal to ms, scale, times mr, rotation, times mt, the translation, which is the typical order you'd want to do it in. You definitely can't put the rotation last, because you'll definitely get wrong results if you do that. And then we can return the interpolated keyframes, keyframe matrix for this bone by returning m, and then our interpolate will return this matrix. Let's go back down to the bottom of this, and we'll add a helper method in here for getting that percentage, get interpolate time %. So this takes in the start time, the end time, and where the animation time is on the timeline. If the animation time is somehow less than the start time, that shouldn't be possible. And if the animation time is somehow greater than the end time, that also shouldn't be possible. In which case we throw this exception here, specifying what value caused the problem. That probably won't happen, but we put that there just in case. If the start time is equal to the end time, that also should not happen. So we got this one here to throw an exception in that case. So under any normal circumstance though, we can just say the current animation time value minus the start time value divided by the distance between the end and the start value. So divided by that full scale. And that will give us a value between 0 and 1 for how far between those two positions it's rotated or is positioned or whatever. One thing that's kind of bugging me is we still have this undefined vertex normal map skin as that vertex type we needed to make, which we're going to need so we can fill in the vertices of our skin mesh. I'm going to go right to the very bottom here and we'll add that in. This one we won't make it nested, we'll make it available elsewhere. So let's stick it outside of all of that. We got the AnimNodes here, and then we got this closing bracket and starting vertex structure. Each vertex has a position and a normal, like most vertices. I'm gonna have this define at the top that we can use. If it is defined using colored vertices, then we can also have this vector for color. Let's go to the very top and add in that definition right above the usings. So as soon as we go into this file, we can see it right away. Since this is now defined, it'll add colors or the color attribute to that vertex. But in our case, or at least in my case, I'm not going to be using colored vertices in most of my stuff, so I'm going to just comment it so that it's undefined. And then down here, because that's undefined, this will show up as black or dark or whatever, because it's not going to add it in when it compiles it. We also need our texture coordinate or a UV coordinate. I'm using a vector 2 and a vector 3 for the tangent and a vector 3 for the bitangent. I'm thinking later on we might change this so that we're only passing in the tangent, and then we can easily calculate the bitangent very quickly on the shader anyway. And I guess same thing too for the weights at least. It's probably possible to have this as a vector 3 and then just say 1 minus whatever the sum of the first 3 are, because you know that the weights always have to add up to a total of 1.0. But no, actually I'm going to keep it as vector 4. I don't want to complicate things. So here we're doing the usual vertex declaration creation technique. And the only thing that might be a bit different that you might not recognize here is the offsets are being calculated using this down here. So a vector 3 is made of 3 floats, and each float is 4 bytes. So you'd use 4 times 3 to get the number of bytes that this would occupy. This is also telling it that it's a position element. And if I pass in 3 into this initialize, this ini thing here, it's using this static method here. It's going 3 times 4 is the byte size, that's 12. Starting byte at 0, which it is anyway. And then it adds that 12 onto here, so it's got the offset for the next time it wants to check. This is going to return 0, so this will be 0 because this starts at 0. But now it knows that the next one has to start at 12. For these off ones, we pass in 3. Byte size is going to be 3 times 4, that's 12. Adds 12 to 12, that's 24. And it's going to remember this as 24 for the next time it uses off. But it's going to return 24 minus 12. So this is at 12. Same sort of idea here. This time it's passing in 2 times 4 bytes, because this is a vector 2 for the texture coordinate. And so this would be 8 plus 24, and then you subtract the 8 from it to get where this one is, and it just continues like that. So that way these entries are slotted into the correct places in memory and given the correct amount of space. So basically whatever you have up here that you're adding in here, you got to make sure to have the same sorts of things here. And when you're accepting your values too in your shader, you want to accept them in the same order. So now we can check in SkinMesh. It knows what this is now, so it's no longer underlined. So now we got all our little structs and nested classes. Now we need to create some methods for our original SkinModel class. Start with a constructor. Now there's always a possibility that we may want to use a different effect for each model, so we'll pass in our skin effects. But we've yet to define what a skin effects is, and we'll need to reference our GPU for drawing. We'll initialize some skin shader matrices for the maximum number of bones that we'll allow on the shader. I'm actually going to call this instead reset shader matrices, which is just going to set all our skin shader matrices to identity matrix for now. Okay, I decided to group the set effect and set effect texture in with the constructor and methods section. In case we want to change our effect or set the texture that the effect uses, we can do that right here. Oh, by the way, this skin effects up here is actually a CS object, a C# object that we haven't made yet, and that's going to handle changing the parameters on our effects. The effect itself, though, we can change that, and we can pass it in with set effect, and we could pass in the camera, the world matrix, diffuse texture. If we want, we can tell it to set the bones, which will pass in the skin shader matrices into the bones parameter. You'll see when we create the effect for this. And optionally, we can set a normal map and optionally a specular map, which makes the surface have a specific type of shine to it. And normal maps, as you probably know, are for that bumpy sort of texture. If we're just setting the effect texture, then we call this method. Pass in the diffuse texture, optionally a normal map, optionally a specular map. So then we pass those parameters into the shader, even these ones if they're not null. Let's add some more space in here. I'm just going to close this region for the constructor and methods. And in here we'll add our updates. in our main update, we have 3 other sub-updates here, which we're going to put down below here. So if the animation's running, we update the model animations, passing in the game time. And we're going to update the nodes, starting with the root node of the tree to update the skeleton animation. And we're going to update the mesh animations. Start with this middle one here, the update nodes, to update the skeleton. I guess technically I probably should do update model animations first. So this method actually assumes that we've already done this update model animations, which determines those local transforms for each bone and their animations. We're going to do that after. First we'll start with, we're kind of doing this backwards, we're going to update the skeleton, pretending that we already did that. So we'll start with the root node here, that's what's passed in initially, and this is going to recursively update the skeleton. If there is no parent, and in the case of the root node, that would be the parent is null, so it's going to skip this and go to the else. Most of the bones, parent is not going to be equal to null because they're going to have parents. So for a normal bone, it's going to combine the local matrix with the parent matrix, starting with the local, ending with the parent, and that way it inherits the effects of the parent and adds on the local bone matrix, offset, rotation, or whatever, and puts that into the combined matrix for this node. And this combined matrix becomes the parent to the next bone down the list. Now if it is the root matrix, it'll do this else because it does not have a parent. Parent will equal to null. So it'll just say combined is equal to local matrix, which will be just that offset from origin to wherever the root bone is. We're going to loop through a flat list of bones for this node. The bone could affect more than one mesh. So looping through the bones, we can get the mesh index and bone index. So I say bn is equal to node.unique mesh bones. That way I don't have to have all this in here. I can just say bn.meshIndex and bn.boneIndex. For each skin mesh, or I should say for each unique mesh bone, we look up which mesh this bone belongs to, and we're going to set the shader matrix in that mesh based on this bone index. So we're going to take that combined matrix, and that's what we're inheriting. That's why we got this multiplied after. And we're going to apply it to our offset matrix. And if you remember before, the offset matrix is basically the offset that gets the bones into their bind position. So now we're applying those transformations and transforming the bind pose to our desired pose, which is stored in this. And we're doing that for each of the applicable bones. And when we're done setting up those shader matrices for the corresponding meshes that these nodes are associated with, we're done with this node, we can go to the child nodes of this node. So we loop through any applicable children for this node and recursively call this method, passing in the child node n. And then that way it'll just work its way through the tree, updating the combinations of the local matrices with the effects of the parents so that everything gets rotated to where it should be. And if any of that seems confusing, that's because it is. Gonna have to visualize it and think about it for a while, or you can just assume that it works and move on. And we kind of did that in a backwards order, so I'm going to add the update model animations next, probably in between these two. Okay, I've added this update model animations for this right here. If the animation count's not valid, or if the current animation is not valid, like it's greater than the total number, then it'll just return. Otherwise, what we're going to do is we're going to update our animation time logic. That'll get the animation frames based on elapsed time for all nodes, and we're going to load them into the model node transforms. Of course, this is underlined because we haven't defined this method yet, but once we've got that logic figured out, we can loop through our animated nodes. So that's our bones and their corresponding keyframes. We'll get the number of animated nodes and loop through those, and we'll reference an animation node based on the current animation and the animation nodes that are associated with that animation. So each one of these is the groups of keyframes for the bones. And each of those keyframe clusters, those AnimNodes, has a node reference. So that's referencing the actual node that is to be animated by that group of keyframes. So we get a reference to that node, and we're just calling it node here. And what we need to do is say node.localMatrix is equal to, and then interpolate the animation for that node, for that animated node. So as you may remember before, we had that interpolate method that we made that was pretty big, and that sets up which frames and so on and so forth, and then interpolates between those keyframes, passing in the animation node and the current animation frame time. And that will return for that animation node the local matrix, and we plug that into this node's local matrix. So we've just created the animation transform, the local animation transform for the bone itself, as though it was at 0. And that local one will eventually be added on to the parent one by multiplying it by the parent. And that's what we do in this update nodes, which is the next step up here. And that's how it puts together the combined matrix for each bone. So this animation time logic, I added the method just below it. The update nodes is now below that one. So we pass into it the game time. We set the current animation frame time to be the game time in total seconds, minus the time start. So we're going to have to set time start at some point when we initialize. And when we get beyond the animation's total duration, the length of the timeline, we'll reset that time start again. Here we set our animation total duration based on the current animation's duration in seconds plus duration in seconds added, so that's extra padding for looping if we want to use that. If we're debugging and we set this override anim frame so that it's something bigger than 0, we can set the current animation frame to be whatever that is. If our current animation frame time is greater than the total duration of the animation, which we calculated here, if it's looped, then we set it to loop. So we go current animation frame time is the current animation frame time minus the total animation duration. And we reset that time start to be whatever the current game time is in seconds, total seconds. If it's not a looped animation, we can just set current frame to 0, time start to 0, so it'll just keep setting this to 0 because this will always be greater than anim total duration, and it just won't run anymore. And animation running is going to be set to false, and because that's set to false, up here where we call this update model animations, it's just not going to call that anymore because it's at the end of the animation. Most of our animations are going to be looped. Okay, so next we need update mesh animations, if there are any regular mesh animations. Now, since update mesh animations is the last step, let's go down to here, and you can see on the bottom in our updates region, I've added this update mesh animations. Now, if there are no animations, it just returns. We'll be looping through the meshes for each animation based on the current animation. If the animated nodes count is greater than 0, basically for each of these, the node with anim trans is indicative that the mesh itself has an animation transform on it. So we're going to set that combined matrix to identity matrix, and as commented here in draw, this should enable us to call on this in relation to the world transform. And you notice here that I'm using current animation index rather than like up here current anim. I could just use current anim, but we're going to add some animation controls down here, and we're going to have a getter and setter for current anim. We could use either one, it wouldn't really matter. Below the updates region, we got this animated controls region now, and we got that current animation index thing here now, which just gets the current anim. We could just put current anim here actually. No reason why not to. But for setting current animation index from outside, for example, we check to see if the incoming value is in a valid range. So if it's greater than or equal to the count, we'll set n to be 0, being the first animation, because an invalid value is provided. And then we just set the current animation to whatever is passed in otherwise. For begin animation, we pass in an animation index, the current game time, so that we can, and this is actually where we're initializing that start time that we compare to up here in our animation time logic. So current animation frame time is going to be whatever the current time is minus the time that we started the animation at, and that's how we know how much time has gone by. So we get that in here where we begin the animation, telling it which one we want, and we set the current animation and tell it animation is running is true because we've started it. We can force the animation to stop by setting animation running is equal to false, and that'll turn off this process of updating model animations up here. Below our animation controls, we'll add a region for drawing. For now, we got this draw method here. Our first draw method will take in the camera, world position and orientation, whether or not to use the materials that are loaded, and whether or not we're going to use the specular material. So we'll loop through all the skin meshes in the object, and for each one we'll set the corresponding shader matrices for that particular skin mesh to the graphics card. So we're sending in the bones, essentially, the bone or positions and orientations. If we're to use the mesh materials, then we'll use the assign materials method, which we haven't made yet. We'll add that down here. And we're going to assign the world position and orientation. Well, this is going to be an identity matrix most of the time, but if there's some kind of position and orientation for like a mesh node transformation, then that can be combined with this to get it to animate its position and orientation according to whatever's going on with that node animation. And like I said, most of the time that'll be an identity matrix. When we create our SkinEffect CS, we're going to need to create a set draw params, which will take in the camera, the diffuse texture we want to use. In this case, we're using the mesh's default, the normal map that we want to use, and the specular map that we want to use. If we set this to false, we could specify our own parameters here, hypothetically, but in the case of this method, we'd have to explicitly assign materials using different materials before we use this draw method. We'll have other draw methods that'll be better suited for that. Here I'm using the GPU draw user indexed primitives, a triangle list type, providing our list of vertices and how many there are, our list of indices, the starting index within that list that we want to use, and how many of those indices we'd like to use. In this case, there's 3 per triangle. And we'll pass in the vertex declaration for our custom vertex that we made. And below this method, we'll add our assign materials. So what we're doing here is we're assigning into our C# file for managing our materials and variables and stuff that are being passed into the shader, and we're just assigning the ambient color value, emissive color value, using the mesh's default material values, as well as the diffuse color. And as you probably know, there is a distinction between the material color values and the textures, which are set up here. If we use the default specular material and the shine strength, then we assign those here. Many times you would want to use that, but sometimes you want to use your own. In our case, we're probably going to use our own. Okay, and so after that, I added this draw mesh method here, and this one's by the mesh node name. Again, we got the camera, the world, same options as before. We'll loop through all our meshes. If we find a base mesh node name that is a match to the desired mesh node name, then that's the one we look for. So we'll say index is equal to I, and we say I is equal to the mesh's length. That basically just breaks it out of this loop. We could put break here instead too if we wanted. If index is greater than -1, so if we found something, we'll go ahead and draw it using our draw mesh. As you may have realized, we don't have a draw mesh yet. We do have a draw up here, so we'll add the draw mesh after this. And I actually just had this below, I just pulled it back up to where you can see it. So I got that one, and I got this one here too, mesh debug draw. This one we might use more often. As I said here, it's great for looping through meshes in the game and specifying unique parameters for each mesh based on what it is. For example, the eyes, I might change the specular values and do something different with transparent materials or different types of textures, different parts of the character. We can customize the specular for each one, for example, and adjust them as we see fit when we're testing the game. It might not be the way we want it or the way we expected. So the materials might not be what we had hoped for. When we created it in our 3D software, it might look a bit different in the game. So this allows us to fine-tune that very easily. First of all, we're passing in mesh index, so we know which mesh it is. We're probably going to loop through the meshes and determine what properties to set based on the names of them, and then we'll call this draw mesh to draw each one individually. We do the same before. We pass in our bone shader matrices into bones. If we are going to use the default materials, then we call assign materials. We set the world. This is probably going to be identity matrix, but it's possible that there's some animated transform on the mesh itself. And this here, again, it sets our parameters. We're doing that just before we do our draw, and this will set the appropriate technique. We'll get into those details on what's going on inside this, which we haven't even made yet, but we'll get into that later. And again, we're just using draw index primitives, triangle list, passing in our list of vertices, the vertex offset, how many vertices there are, the index list, the starting index, how many indices there are, which is going to be divided by 3 because we need the primitive count here, which is the number of triangles. In the debug version here, we loop through the meshes, use the default materials, and we check to see if the index in this loop is the mesh ID to show, which is the one we're trying to debug. We'll set its world parameter. In this case, we're just directly applying the effect, and it doesn't seem like we're setting up our textures, and then just drawing that particular submesh from the character. So like maybe it's just the hair or something like that. I haven't actually tested out this mesh debug draw yet, but it's here and we could modify it if we find that there's something missing from it or it's not working the way we expected. So in our example, we're mostly going to use this one, draw mesh. For just basic drawing of a character, we might want to use something like this. But I'll show you more about how we're going to use this later. So right now we don't have this SkinedEffect, this C#. We're going to need a SkinedEffect shader, so we kind of know what to expect for passing parameters to it. Do it like this. Go into Content, Content Builder, and say File, Add, go Edit Add, New Item, go Effect.fx, and we'll change the name of this to SkinEffects, I guess. Or no, we'll make it different from the C# class. We'll call it SkinEffect, and create. And I'll use Open With 2019. Okay, I'm going to change these versions to... You don't have to change these. This is a DirectX 9 compatible version, regular shader level 4. So this 9 compatible version is more like shader 2. If you strip this off, that's actually shader 4. And we're going to go with 5. I added this max bones of 180 right at the top here. So let's add 3 textures up here, a diffuse texture, normal texture, and specular texture. And the normal map and specular map will be optional. So in S0, our parameter that we're going to pass into is going to be text diffuse. For a normal map, I'm calling it text normal map, and for specular, text specular. So we may want to write that down so we know what the parameters are actually named. I'm using anisotropic filtering. That's for very smooth blending and sampling. And for if it goes outside of the UV bounds, it'll start mirroring those coordinates. I probably should do the same instead of a wrap for the normal map, or clamp. I think a lot of times people use clamp. I'm going to use mirror. Because I mean, if we use wrap and it starts sampling the bumps from the opposite side, it might look a little bit weird. But we'll probably never see it go outside the UV bounds anyway. This is just sort of just in case. And you'll notice here I set min filter linear, mag filter linear, and MIP filtering anisotropic. For the diffuse, I just set them all to anisotropic by saying filter equals. So that would set all 3 of these. And we could leave this as matrix, which I believe is float 4x4. I'm going to call it float 4x4 just because it's very explicitly clear, because it's possible to have a 3x3, for example. Our matrix that gets our world coordinates will be here, and this will be combined with the world view projection transformation. For our normals, we're going to use an inverse world. So I'm going to call it world inverse transpose. So that's the world inverse transpose matrix. And we're going to use that on our normals. If we've got any kind of scaling, this will make sure that our normals are going to be correct. If you're not sure why we use the world inverse transpose, I suggest actually looking this up. Look up this keyword on Google and normal and how it's derived, what it's for, and why we're using it on our normals. It kind of take me a little bit extra time to explain here. A lot of people probably already know this, so I'm just going to move on from this one. But the idea is, if you have any kind of non-uniform scaling here, our vertices, for example, are being moved around and stretched around quite a bit, so our normals are not going to be very accurate. Certainly not like a static mesh. If it was a mesh that isn't transformed or stretched or anything like that, then we could definitely get away with not using the inverse transpose, like for a landscape or something like that, something that doesn't move or distort or anything like that. And we're also going to need to calculate our lighting of what our camera would see, but to do that we got to know where the camera is. So we're going to get our camera. I'm going to call this cam position, cam pose. Next up, we'll need to add our material properties that we may want to pass in. I guess we could call this material and lighting. So we got our diffuse material. That's the regular color of the material. Provided there's no texture on it, it would just use this color. Got the emissive color. We'd normally have an ambient color in here too, but that's already been factored into emissive color. So the two of them are kind of combined here. And we're going to do that in our SkinEffects C# class. And then we got our specular color. That's the color of the reflecting light. And the specular power. I would also remind that you can lower the values in your specular color to reduce the strength of the light also. And we got our shine amplifier here. I'm only using that for my character's eyes. It's just a custom thing I'm doing. And we have 3 optional lights here. I'm probably going to do this that all 3 are just assumed always to be turned on, just to simplify the code a bit. That way, if we want, we can set up kind of a nice 3-point directional lighting. For the main character, we might not use the fog, but we'll probably use it for other characters. So we'll keep the fog in here. And then we got our list of bones here. This is technically separate from these. It's not part of the material, so I'll just put space between those two. And the number of bones we can use we defined up here already. First thing we'll need is our vertex shader inputs. So these are the default ones. I'm going to change this so it's more suited to what we're trying to do. I just shortened the struct description to VS in, so vertex shader in, instead of the longer version. We're going to take in a float 4 for the position, color 0 if we were using it, but we're not using it, so I commented that out here, but it's possible we'll use it in the future, maybe in a different type of project. So I'm just going to keep it as a comment here for now. Next, we're taking in a float 2 for the UV or texture coordinate, float 3 for the normal, float 3 for the tangent, float 3 for the bitangent. Now we may end up actually abandoning this, and then we'd have to change our vertex declaration too, because we'll probably end up calculating our bitangent in here. Then we got the indices to the 4 bones, and float 4 for the 4 weights. It might even be possible too to use the float 3 for weights and then just say 1 minus the sum of the first 3. But I think I'm just going to leave it as passing in the 4 weights. Next we'll move on to the structure for the vertex shader output. I'm going to create 2 of them to replace this one. So the regular one we have down here takes in the position, UV coordinate, the world position, so we can use this one. We can't use this one. This is for the hardware. And the normal. And for our normal mapped one, float 4 position, usual texture coordinate, float 4 world position in texture coordinate 1. And we got a float 3x3 for our tangent space, and we're going to put it in text coord 2. Shortly I'll show you how to use this tangent space transformation with your normal map so that you can get the correct normal map lighting across the surface using a normal map. And again, I commented these out because we're not doing any color shading across the surface for the time being, at least not in this version of the project.